Have you ever wondered how the sun generates its energy? The answer is both incredibly complex and beautifully simple. It all boils down to a process called nuclear fusion, the very same process that powers the stars scattered across the cosmos. Now, imagine a dance, a cosmic ballet of atomic particles. The dancers are light atoms, hydrogen to be precise, the most abundant element in the universe. These particles, small as they are, hold immense power. Under the phenomenal pressures and temperatures at the heart of the sun, these hydrogen atoms are forced to come together to collide, and when they do, something extraordinary happens. They fuse, they merge, they become one. This fusion creates a heavier atom, helium, and in this process a vast amount of energy is released. But this isn't just any energy, it's the energy that lights up our days and warms our world. It's the energy that fuels the sun and stars, making them shine brightly in the vast expanse of space. This energy, my friends, is the product of nuclear fusion, a process that takes place in the sun's core, some 93 million miles away from us. For decades, scientists have been captivated by this process. They've wondered, pondered, and dreamed about harnessing this power, about replicating this fusion here on Earth. The potential is staggering. Theoretically, nuclear fusion could fulfill all of our planet's future energy needs. It could provide us with a clean, virtually limitless source of power. But achieving this is no small feat. It requires overcoming the natural repulsion between positively charged atomic nuclei, a task that requires incredibly high temperatures and pressures. The sun's power comes from an incredible process called nuclear fusion, and scientists have been trying to replicate it on Earth for decades. The journey is fraught with challenges, but the potential rewards are too great to ignore. On this quest for a brighter, cleaner future, every step forward brings us closer to unlocking the power of the sun. Replicating the sun's energy production on Earth is no easy task. You see, nuclear fusion is a bit like trying to force two positively charged magnets together. They naturally repel each other. This is the fundamental challenge we face when we talk about nuclear fusion. To make the fusion happen, we need to overcome this electrical repulsion between the positive nuclei of the light atoms we're trying to fuse. This repulsion is a result of something called the Coulomb force, a fundamental force of nature that causes like-charged particles to repel each other. And let me tell you, overcoming this force is no small feat. The temperatures and pressures required to overcome this electrical repulsion are immense, far greater than anything naturally occurring on Earth. We're talking about conditions like those found in the heart of the sun or in the core of a star. To give you an idea, we need temperatures of around 100 million degrees Celsius to initiate nuclear fusion. That's hotter than the core of the sun itself. In the past, scientists have tried various methods to achieve these conditions, including using strong magnetic fields and powerful lasers. But despite their best efforts, these methods have not been able to generate more energy than they consume, which is the key to making nuclear fusion a viable energy source. Furthermore, even if we manage to overcome the electrical repulsion and initiate fusion, we need to ensure that the energy released is enough to drive the fusion of nearby nuclei, creating a chain reaction. This is known as ignition, and achieving it is another significant challenge. But let's not forget, the prize at the end of this uphill battle is nothing short of monumental. If we can harness the power of nuclear fusion, we could potentially solve the world's energy problems. We would be using the same energy source that powers the sun and the stars right here on Earth. The hurdles are high, but the rewards are potentially enormous. Imagine an Earth powered by the same energy source as the stars. Recently, scientists at Lawrence Livermore National Laboratory's ignition facility made a significant breakthrough. An extraordinary leap that, for the first time, saw a fusion reaction producing more energy than it consumed. Let's delve into that a bit more, shall we? Imagine a powerful laser with a staggering energy of 2.05 megajoules, pulsating with a force that can only be described as otherworldly. This is not science fiction, but a reality that scientists at the Lawrence Livermore National Laboratory made possible. They use this prodigious laser to initiate nuclear fusion. Now, nuclear fusion is a process that's been studied for years, but never quite achieved in the way we've hoped. It's the very process that powers the sun and the stars, a seemingly infinite source of energy that we've longed to harness. But until now, every attempt to initiate this process on Earth consumed more energy than it produced. However, this groundbreaking experiment changed the game. The laser incredibly triggered a fusion reaction that generated 3.15 megajoules of energy. That's more than it consumed, marking a turning point in the history of nuclear fusion. Now, this is not about building a miniature sun here on Earth. It's about creating a sustainable, practically limitless source of energy that could revolutionize the way we power our world. This breakthrough is a monumental step towards that goal. But of course, it's important to remember that this is just the beginning. It's one thing to generate a net gain in energy in a controlled experiment, and quite another to translate that into a working power plant. There are still many hurdles to overcome, from scalability to plant safety, before we can harness the full potential of nuclear fusion. Nevertheless, the impossible has been made possible. We've taken a step closer to the stars, and the energy that powers them is now within our reach. This landmark achievement marks a new era in the quest for nuclear fusion. While the breakthrough is monumental, it is only the beginning of a long journey. The road to a future where nuclear fusion powers our world, much like it powers the sun and stars, is fraught with challenges that scientists and engineers are still grappling with. One of the primary hurdles is scalability. The ability to generate net energy from nuclear fusion in a controlled laboratory setting is a remarkable achievement. However, scaling this process up to a size where it can power entire cities or even countries is a task of a different magnitude. It requires not only advancements in technology, but also significant investment in infrastructure and resources. Then there's plant safety. Nuclear fusion, by its very nature, involves the handling of high-energy particles and extreme temperatures. Ensuring the safety of those working in and living around potential nuclear fusion plants is paramount. This will require the development of stringent safety standards and protocols, as well as advancements in material science to withstand the harsh conditions inside a fusion reactor. Another major challenge lies in the energy required to generate the laser used to initiate the fusion process. While the recent breakthrough saw more energy produced than consumed, the energy required to start the process is still considerable. Finding ways to reduce this initial energy requirement without compromising the fusion process is a key area of ongoing research. And let's not forget about the byproducts of nuclear fusion. While fusion is cleaner than its cousin, nuclear fission, it still produces some waste. Managing this waste in a way that is safe and environmentally friendly is a significant challenge that needs to be addressed. A fully functioning nuclear fusion plant may still be decades away, but each step brings us closer. Each challenge overcome, each milestone reached, brings us one step closer to a future where the power of the sun and stars can be harnessed here on Earth. And that is a future worth striving for. The ignition of nuclear fusion is a major milestone in the pursuit of a cleaner, more sustainable energy future. This recent breakthrough signifies a monumental leap forward in the world of science and energy production. It's not just about creating a new power source, it's about redefining the way we approach energy and ultimately, our relationship with the planet. Nuclear fusion, the process that lights up the stars and our sun, has long been a dream for scientists and energy experts alike. It's a form of energy that's clean, abundant, and incredibly powerful. The potential of nuclear fusion, if harnessed correctly, could meet our planet's future energy needs in a way that's sustainable and environmentally friendly. Imagine a world where energy is no longer a scarce resource, where the fear of depleting fossil fuels is a thing of the past. A world where the energy that powers our homes, our industries, and our cities is virtually inexhaustible. That's the promise of nuclear fusion. But let's not get ahead of ourselves. The road to this utopian energy future is still long and fraught with challenges. There are significant hurdles to overcome, including scalability, plant safety, and the energy required to generate the fusion process. Each of these issues requires extensive research, development, and testing before a functional nuclear fusion plant can become a reality. Yet, the ignition of nuclear fusion is a beacon of light on this journey. It's proof that we're heading in the right direction, that the dream of harnessing the power of the stars is not only possible but within our reach. This breakthrough serves as a foundation upon which future progress can be built, a stepping stone towards a new era of energy production. The dream of harnessing the power of the stars is closer than ever before. The journey is tough, but the destination is worth it. And with each step we take, we move closer to a future where clean, sustainable energy is not just a possibility, but a reality.